Very often, a switch to cylindrical coordinates can simplify the description of a region, which in turn simplifies the evaluation of an integral. So we'll take a look at some examples of how to evaluate triple integrals in cylindrical coordinates. This integral given below would be very difficult to evaluate as is. However, if we switch to cylindrical coordinates, we'll find that this is quite manageable. We need to pay attention to what the region of integration is. So here we're told that z is evaluated from -1 to 2, and this is the inner integral, so it's being described as a type 1. Y goes from negative square root 8 minus x squared to positive square root 8 minus x squared, and then the value of x goes from 0 to 2 root 2. Now remember that this is root 8. Because this is a type 1 integral, this is this projection d. We are projecting it onto the xy plane, this z equals 0. And if we examine these other limits, what we're going to find is that x goes from 0 to root 8, whereas y is the right half of a circle, which is just a semicircle of radius root 8. So it's possible for us to describe this in cylindrical coordinates. The radius goes from 0 to root 8, angle goes from negative pi by 2 to positive pi by 2, and the z value will go from -1 to 2. The other thing that becomes very useful is that the description of this function is quite straightforward. We've got a square root of 1 plus r squared. So this integral now reads as follows. Negative pi over 2 to positive pi over 2 in the theta, 0 to root 8 in the radius, -1 to 2 in the z. We'll have 1 plus r squared. Remember that this factor of r needs to be present, dz, dr, d theta. By Fubini's theorem, it doesn't matter what order we put these integrations in. So as written, we'll be integrating in the z direction first. This will simply be zr times this square root, evaluated from -1 to 2, which will in turn just give us a 2 minus -1 times r into this square root. So this will just be a 3r into this square root. So the integral simplifies. We'll have the following. 3r into 1 plus r squared dr, and then d theta. Remember that this entire integral will be a constant, and as such, we can take it outside of the theta integral. At the end of the day, what this produces is an integral 0 to root 8, 3r into this square root dr, times an integral negative pi by 2 to positive pi by 2, 1 d theta. We can treat these integrals separately. In this first case, what we'll have is u as 1 plus r squared. Du will be 2r dr. When r is 0, u is 1. And when r is root 8, u will be 9. This integral here is dead simple. This is just going to give us a theta evaluated from negative pi over 2 to positive pi over 2, which just ends up giving us pi over 2 subtract negative pi over 2, which is just pi. What we'll now have is 3 square root of u du over 2 evaluated from 1 to 9, and this will multiply by pi. This produces a 3 over 2 u to the 3 halves over 3 over 2 evaluated from 1 to 9 times pi. The 3 halves and the 1 over 3 halves will cancel. I'll have 9 to the 3 halves minus 1 to the 3 halves times pi. This is saying square root of 9 cubed, which ends up being a 27 minus 1. So this produces 26 pi. As before, if our function is identically equal to 1, then this triple integral simply produces the volume of the region E. Now, this is really helpful because we can now come up with results from geometry that we've seen before. Let's use triple integration to determine the volume of a cone that has a height of h and a radius of a. So something that looks like this. If we overlay it on our axes, this has to be a, and this value here is h. Remember that the simplest version of a cone is x squared plus y squared with this square root. It simplifies nicely to just square root of r squared, which is just r, because we're always taking a positive radius. But unfortunately, we have no control over the radius versus the height here. So what we need to do is use a scaled version of z, so this is like a dial, and set it equal to r to get the proper relationship between the height and the radius. So when z is equal to h, this is going to correspond to r equals a. So if we sub this into our equation, we'll have h times this dial is a, so clearly this dial has to produce the value of ah. The proper cone description will be a over h times z is r. This cone is z is h over a times r. We're going to talk about this as a type 1 integral. So this height, z is h, and at this bottom height, z is h over a times r. Once we describe it in that type 1 region, we're going to have to project this solid down onto the xy plane to get this other region D. So the limits of integration here for z will be from h over a times r up to h. The volume will be a triple integral over this region 1 dv. We're now going to have an integral over d and then an integral in z where we go from h over ar up to h dz times this dA. This region here is this projection. And so this is the shadow of this cone when we shine it down onto the xy plane. The radial limits will be from 0 to a, and the angular limits will be from 0 to 2 pi. This allows us to further rewrite this integral as 0 to 2 pi, 0 to a, h over a times r up to h, 1 dz, and then we'll have this r dr d theta. We can put this r in or out, it doesn't really matter, but the r value must not be outside of this dr. It has to happen while we do this r integration. So we're able to rewrite this as an integral 0 to 2 pi, integral 0 to a. This will simply produce a z from h r over a up to h r dr d theta. This will get a 0 to 2 pi, 0 to a, h minus h over ar times r dr d theta. As before, this entire expression here is a constant with respect to theta, so we can take it outside of the integral. This will produce an integral 0 to a, h minus hr over a times r dr multiplied with an integral 0 to 2 pi d theta. This is just going to produce a theta evaluated from 0 to 2 pi, which is just 2 pi. This, if we expand out, we'll get an hr minus an hr squared over a dr. This will give us an hr squared over 2, hr cubed over 3a, evaluated from 0 to a. This will be ha squared over 2, ha cubed over 3a. One of these a's will go away. This will give us 2 pi 3 ha squared over 6 minus 2 ha squared over 6. This ends up giving us a 2 pi ha squared over 6, which then produces the familiar result that the volume of a cone is 1/3 pi ha squared. Let's come up with the mass of a volume that's bounded by a cone, z equals square root of x squared plus y squared, and a paraboloid, z equals 12 minus x squared minus y squared, if the density is a constant. The mass is always equal to the integral of the density over that entire region, but if the density is a constant, this simply boils down to determining the volume of our region. We are going to convert this to cylindrical coordinates. Now note that the cone can be described by z equals r, and the paraboloid can most easily be described as 12 minus r squared. So what we need to do is find the intersection of these. So we set the values of z equal to each other. We'll have 12 minus r squared is equal to r, or r squared plus r minus 12 is 0. That gives us an r plus 4 or an r minus 3 is 0. So the solutions would be r is 3 or -4. This one we reject because r values for us will always be positive. And that lets us draw this region. So in the z-axis, we will have a paraboloid that intersects this cone. So our cone will go up to a height of z equals r, which is 3. And then the paraboloid will sit on top of it, almost like ice cream. So we want to figure out the volume of this region. Now, this is most easily described as a type 1. We are going to integrate first parallel to the z direction. So this will give us a 12 minus r squared, whereas this will give us an r. So z will be trapped between those two values. What we then need to do is project this down onto the xz plane. So this will be our region D. So the volume of this region will then be a double integral over D, an integral from r to 12 minus r squared. We'll have a dz, and then we'll have this dA. To describe this properly, we are going to be in the xy plane. So this is where z is equal to 0. But in this case, we already know that the radial value will go from 0 to 3, and the entire angular value will go from 0 to 2 pi. So the volume then becomes the following. It will be an integral from 0 to 2 pi, 0 to 3, r to 12 minus r squared, dz, r, dr, d theta. This simply produces a 12 minus r squared subtract r. So we'll have an integral 0 to 2 pi, integral 0 to 3, 12r minus r cubed minus r squared when we incorporate this r factor inside. As before, this is simply a constant with respect to theta. We can take it outside. And this produces a product of two separate integrals. 12r minus r cubed minus r squared dr times the integral 0 to 2 pi d theta. This will produce a 2 pi. This is going to give us a 12r squared over 2, r to the 4 over 4, r cubed over 3, evaluated from 0 to 3. All of this times 2 pi. This will give us a 6 times 3 squared minus 3 to the 4 over 4, subtract 3 cubed over 3 times 2 pi. We'll have 54 minus 81 over 4. 3 cubed is 27 over 3 will produce a 9 times a 2 pi. This is going to be 45 minus 81 over 4 times 2 pi. This is going to be 180 over 4 minus 81 over 4 times 2 pi. This gives us a 99 over 4 times 2 pi, which is a 99 pi over 2. Therefore, the mass is the integral of the density over this region E. We knew the density was constant. All we needed to do was find the volume of this region, so we end up getting a 99 pi rho over 2 as the mass of this region.